Electron configuration, let's go. I'm going to try to be excited about it because I feel like if you're watching this video, maybe you're not excited about electron configuration. So in this video, there are going to be 3 parts, actually maybe 4, perhaps that 3 was a lie. So at the very beginning, these first couple slides, I'm just going to orient us to the periodic table and make sure we're all on the same page about how we look at the periodic table and how the regions of the periodic table correspond to different types of orbitals that we've been talking about that we need to know when we're writing electron configuration. And then in the next step, or the next section, I'm going to practice with you guys writing electron configurations for elements using just the periodic table. And then the next section will be using that Aufbau diagram to write our electron configurations. And then the last part will be on noble gas configurations. So I'll put timestamps in the video in the description box so that if you want to focus on just one of those aspects, you can skip ahead and not listen to me ramble for this whole video because I'm not sure how long it's going to end up being. Okay, so let's get started. So the first step that we said that we were going to do is just take a look at a blank periodic table and see which parts of this table correspond to which types of orbitals that we've been talking about. So remember, the 4 different kinds of orbitals that we have are s orbitals, which are spherical, p orbitals, which have a dumbbell or a peanut shape, d orbitals, which kind of look like a 4-sided flower, kind of 4-leaf clover maybe, and f orbitals, which look like a more complicated flower, and we're not worried about the f orbitals. So those can kind of just like, you can ignore those guys. So when we're looking at our periodic table, we can think about the different blocks of the periodic table as corresponding to those different kinds of orbitals. So here, this first region that I'm outlining here is going to correspond to the s orbital group. And actually helium, even though it's over here on this side, also belongs to this s group. So it's weird, like it's up here on the top by itself, and you can see that there's this little empty nook over here. So mentally, you can sort of just like shift helium over into that empty space for the purposes of electron configuration, at least. Okay, so I just noticed that there's an error on this periodic table, but I've made too many slides, so I'm going to ignore it for now. Sorry, the numbers here are wrong. It should go 1, 2 for helium, 3 for lithium, 4 for beryllium, and then that way 5 is boron. So if you're distracted by that, I'm seeing that now, and it's definitely, the periodic table is wrong. You're not wrong if you saw that. Okay, so s orbital over here on this far left side, and then the next one that we'll talk about is the p orbital, which is over here, this block on the far right-hand side. So this area corresponds to our p orbitals. And the next one is the d orbitals, which are going to be this block here in the middle. So these guys are the d orbitals. And then last but not least, even though we don't care about them so much, I will just, for the sake of having a completely colored table, highlight these ones down here, which correspond to the f orbitals. So the one thing that I want to point out in this particular slide is that maybe you've noticed that all of these blocks are different widths, and the width of each block is going to correspond to the number of electrons that that block can, or that type of orbital can fit if it's full. So remember that s orbitals are spherical and they can only hold 2 electrons. So that's like a sphere, s, and s orbitals can fit 2 electrons. And if you look at how wide, or how many elements wide this s block is, it's 2 elements wide. So lithium, beryllium, that's 2 elements, potassium, calcium, that's 2 elements. So the s block is 2 elements wide, and s orbitals can fit up to 2 electrons. And the same pattern is going to hold true if we go look at the other types of blocks/orbitals. So this p orbital block over here, remember p orbitals can be either horizontal, they can be vertical, or they can be sort of along the z-axis where one side of it is facing you like from your laptop screen and the other side is going behind your laptop screen. And so there are 3 different p orbitals and each orbital can hold 2. So we know that our p orbitals altogether can hold 6 electrons. And when you look at the p orbital block, each block in this p section is 6 elements wide. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So the p element, p block of the periodic table, just like the p orbitals, are 6 elements wide. And then I won't belabor the point, but the same thing is going to hold true for the d block. So d orbitals are those 4-leaf clover looking ones, and there are 5 of them. And so 5 orbitals, each orbital can hold 2 electrons, which means that the d orbitals, if they're all full, can hold up to a total of 10 elements. And if you go across, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the d block can hold up to 10 electrons, or the d orbitals can hold up to 10 electrons. Okay. So I'm going to move us forward to a slide that basically shows the same thing. I tried to keep it colored consistently with what I was doing with the highlighter, and it's just showing it in a little bit more neatly organized way. So we still have the S block over here on the left, the P block over here on the right, and the D block here in the middle. So one thing that this tape or this graphic is showing you that I didn't call attention to on the previous slide is these numbers before each block type. So we were talking about the S, the P, the D, and now we've got numbers in front of them. And you can see that these numbers correspond to the periods of the periodic table. And remember, the periods are just going to be our rows going across. So first one on top is the first period. And we can also think of this as corresponding to the first energy level. So remember, we were talking about as you get farther and farther away from the nucleus, your energy level is going to increase, and you're also going to have more energy associated with those electrons. So this is shown on the periodic table by the period that you're talking about. So first period on top, and then the same way that you would go to the next line if you were reading a book. So like going across the same way that if you're reading a book, you just go across. So first level, and then second level, and then third level, and then fourth level. And you might notice that there's a little bit of weirdness that happens right here. So we talked about for each energy level that you go up, unlocking a new kind of orbital. So we said that when you start off, you're at the first level, the first energy level, all you have is s orbitals, and that's sort of like your default. And then we said that when you get to the second level, you unlock p orbitals, and that's why you can see that we start having p orbitals over here on the second level. And then we said that at the third level, you unlock d orbitals. So you might expect that the first d orbital should be right here. But there's a weird thing about the d orbitals where they actually don't start until after the fourth energy level. So there's this weird jump where there's nothing happening for the d subshell on the third level. But once you get to the fourth level, that's where the d orbitals are going to pop up. And that's a pattern that's just going to hold true with any d orbital. It's always going to have a number in front of it that is 1 less than the energy level that you're on, than the period that you're on. So if you're on the fourth period of the periodic table, this fourth row, you're going to have d orbitals, but they're going to be the 3 d orbitals, 1 less than 4. And the same thing, if you're on the fifth level of the periodic table, you'll still have d orbitals, but those are going to be 4d orbitals because it's going to be 1 less than the level that you're on. So that's just a quirk about d orbitals that we just have to embrace and work with. And I think dealing with it becomes easier if you just practice a little bit. So that'll be what we'll do for the next few slides, just practicing with just a periodic table, how we can figure out these electron conformations. Okay, so I circled beryllium, and I'm really regretting using this table now. If I felt more motivated, I would go and redo this whole thing, but I'm too deep in it. So mentally, let's correct this table. Beryllium, you should know that if you count the number of electrons, they should go up by 1 for each element. So hydrogen is 1, helium has 2 electrons, lithium has 3, and beryllium should have 4. And that's the number of protons and the number of electrons that beryllium has. So when we're thinking, I'm going to switch to a pen. When we're thinking about writing our electron configurations using just the periodic table, we just have to keep in mind those blocks that I just talked about. So remember, helium is in the S block, even though it's over here, and we're going to read in the same way that we would read like a book, from left to right, from top to bottom. So starting here and going across, we just covered the 1s orbital, and we filled it up, so there's 2 electrons there. And now that we're going to another row, another period, we need to continue, but this time we're in the second row, the second energy level. So we're starting with a 2, and we'll always start with this. We're in the S block here to start with, and we could say there's 2s1 here. That's not a 6, that's a circle. And then 2s2 here. So 2s2, and then we're done, because we were just trying to get to beryllium, and we finished there. We've got 4 electrons, which, remember, we are mentally correcting beryllium to have 4 electrons. So that adds up, and we're all good on that front. So that's a relatively simple one to start with. Let's take a look at something a little bit more complicated. And by here, all of the atomic numbers and the number of electrons are correct again, so we don't have to worry about our messed up periodic table. Okay, so we're going to do this the exact same way. We're going to start up at the top with the first period, the first energy level, and go across. So this is 1s2, and we filled it up. So now we're going to go to the second energy level, and we can see that we filled up our 2s2 energy level. And then this is the P block, remember? So we're going to just go right across, and we filled up the P orbitals as well. So that's 2p. And hopefully you remember that if it's a full p orbital situation, that's 6 electrons. But if you forget, you can just count the number of elements here. So 1, 2, 3, 4, 5, 6. So we filled up all of those, and we did 2p6. And then we go down to this next row, which is the third row, and we can say 3s2, because we're in the S block here, and then keep just going across. And so now we're in the 3p block, but you can see this is where we're going to stop, because sulfur's in this block. So we only want to go as far as sulfur is. So we're going to say 3p is where we're at, and we want to say 3p1, 3p2, 3p3, and 3p4 is where we finish. So 3p4. And if you add up these electrons, if you wanted to double check your work, 4 plus 2 plus 6 plus 2 plus 2 is going to give us 16, which is the number that is the number of protons that sulfur has, and therefore also the number of electrons that sulfur has. Okay, so let's go into one that's a little bit more difficult, because we're dealing with the d orbitals now. So this is cobalt, and we're going to do the exact same thing as we did before. So starting off, going across, this is the 1s2, and then we've got the 2s2 here. We keep going across, and we filled up the 2p level, so that's 2p, and we did all of them, so it's 6. Then we've got the 3s2, and again across, and we filled up the 3p level, so that's 3p6. And then here again, we're going to keep going down. So we just finished the 3p's. We're going to go here and say we've finished the 4s2 level. 4s2. And if it helps for you to number these rows or periods, that can be helpful too. Okay, so here is where it's important not to get tripped up. So here we've run into what we know is the D block. But remember, the D block is weird in that it's always going to have a number before it that's 1 less than the row that we're dealing with. So we're in the 4th period, but when we hit this D block, it's going to be 3D. So just always take one integer, one number off from wherever you're at. So after we figure out that one little trick, it's the same thing as we have been doing. We know that we're in the D block, that's where we want to be. So we're just going to count until we get to cobalt. So we're 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7. So 3D7, and that's it. So as long as you can remember that when you're doing the d orbitals, just take one letter off, or sorry, take one number off, subtract one, you're good to go. And it's otherwise it's just the same as going across from top to bottom and from left to right. Okay, let's do one more really, really complicated one. I'll have to talk a little bit faster for this. Otherwise, I think this one orbital alone would take me 10 minutes. So we're doing antimony down here. So again, across, that's 1s1. Oh, sorry, 1s2. We did 2. And then 2s2, 2p6, 3s2, 3p6, 4s2, and then remember it's 3d10. And again, hopefully you remember that the d orbital holds 10 electrons, but if not, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So you know it's 3d10. And then again, we're totally filling out this P block. And then once we're out of the Ds, we're going to go back to 4. So it's going to go back to 4P. So 4P, because we're on the 1, 2, 3, 4th period or 4th energy level. So once we get back to the Ps, there's no more weirdness. We're going to go back to our 4s. And we've got all 6 of them there. And then we go down to the 5th level, 5th energy level, 5th period, and we've got 5s2, that's here. And then again, same thing. We're going to go to the d orbitals now, but we're going to take one number off. So we're 4d instead of 5. And again, we've got all 10 of them. So 4d10. And finally, we've gotten to, again, we're in the 5p level because we're going back up to 5. And we finally arrived, 5p1, 5p2, 5p3 is our full electron configuration for antimony. That was a really long one. So for that one, the noble gas configuration, which we'll talk about at the end of this video, would probably have been much more convenient. Okay, so now we're going to switch gears and just use a different strategy to do our electron configurations. So we're going to be using this Aufbau diagram, which, if you don't remember, is this guy that looks like this over here. So when you're using these diagrams, you would just always want to follow the arrows and start from this non-arrowhead side, follow the arrow down, and then jump to the next non-arrowhead side, go down, jump to the next non-arrowhead side, go down, etc., etc. So with this method, you have to be a lot more careful to know how many electrons are going to fit into each orbital. So you have to know that the s orbitals, if they're full, can hold 2. The p orbitals, if they're full, can hold 6. And the d orbitals, if they're full, can hold 10. Because what we're going to be doing with this method is just some like accounting where we look at the number of electrons that we need to take into account, and we'll just stop once we get to that number of electrons. So let's look at an example with fluorine, which has 9 electrons. So with this method, what you're going to do is you're just going to follow these, follow this order in the way that it's presented with the arrows. So you can see we're starting with 1s, and like I said, 1s is full, it's got 2 electrons. So we need to get to 9, so we need to keep going. So we did 1s, and now we're going to the next one, which is 2s. So 2s, and again, s orbitals hold 2. We've only got 4 electrons, we need to keep going. So we get next, here we're at the 2p. And so p orbitals, remember, can hold 6 electrons. So if we put in all 6, we would have too many because 6 plus 2 plus 2 is 10. Here we have, here we have 4 electrons, and since we need 9, we need 5 more electrons. And so this next 2p level, we only want to put a 5 because that will give us a total of 9 electrons, which is how many fluorine has. So here we're not going, like, we're not reading the periodic table in the same way. We're just using this sort of shorthand guide chart and doing some accounting for the number of electrons. So let's do another example. So you have to be good with addition to do this one, but it involves less fiddling with the periodic table itself. Okay, so let's look at iron, which has 26 electrons. So we're going to do the same thing. 1s can hold 2, and then jump over to 2s, which can also hold 2. 2p can hold 6. So at this point, we've got 10 electrons here. And remember, we need to get to 26. So we have still a ways to go. 3s, 2. And then, so 2p, 3s. The next one here is going to be 3p, 3p, 6. And here, let's see, we'd have 10. We've got 18 now. So we still need to keep going. 4s, 2. That's 20. And then 3d. So that could fit up to 10. And let's see where we're at. I said this is 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18. We're at 20 here, and we only need 26. So like at this block, we had 20 electrons, we need 26 electrons. So that means in the 3d orbital, we only want 6 electrons. So again, a little bit more accounting with this method, but you don't have to fiddle around with the periodic table. Let's do one more. This is, I don't know if my math skills are good enough late in this game, even though it's just addition. So let's try to see if I can do this without messing up. Okay, 1s2, 2s2, 2p6, oops. How do I, sorry, 1 second, let me erase this. Okay. 2p6. So we did 1s, 2s, 2p, and I'm just going to make a little mental note for myself that we're at 10 electrons here. So 2p6, and the next one is going to be 3s2, and then if we keep going, we're at 3p, 3p6, and then if we keep going, 4s2, and I'm going to make another little mental note for myself that here we're at 20 electrons. Okay, so we did 3p, we did 4s, next is 3d. So that's 3d, and remember the d orbital, if it's full, can hold 10 electrons. So here we're at 30 electrons, and we need to get to 38. Okay, so 3d, and then the next one is 4p, 4p, and we can hold 6 electrons there. So here we're at 36 electrons, and we need to get to 38, so we need 2 more. So we did 3d, we did 4p, the next is 5s. And that's perfect, 5s2. And if you feel comfortable with both methods, then you can, it's nice to double check yourself. And we ended with 5s2, and you can see based on the position of strontium in the periodic table, we're on the 1, 2, 3, 4, 5th period, and we're in that s2 position in the s block, because this is the s1 position and this is the s2 position. So everything checks out, and you can kind of mentally double check your work that way. Okay, I'm gonna skip over this one because I feel like I've exhausted my mental math, and I think you probably get the point. The flipping between the 4s 3d, 5s 4d is less of a, like, you don't have to think about it as much with this method. And then the trade-off is more mental math and keeping track of how many electrons you've already taken into account. So I'm gonna skip that one. And we are instead going to go into this shortcut method where we're using the noble gas configuration. So this group right over here on the far right-hand side are the noble gases. And we're going to use these to make our life easier. As you probably could start seeing with those other examples, these electron configurations are starting to get really long and a pain in the butt to write. So basically, we're going to skip some of the earlier steps by putting a stand-in, and the noble gases over here are going to be our stand-ins. So how does this work? Let's look at magnesium, and I want us to start by just writing the normal configuration, like the full electron configuration for magnesium. So this shall be easier for us now because we've just gotten like way farther and we don't even have to deal with the D's, but so let's go across. We've got 1s2, we've got 2s2, 2p6, and then 3s2, and that's magnesium. And so what the noble gas configuration does is we're going to look for the previous noble gas. So we can't go forward, we have to read backwards. So I was saying that normally if you're reading the periodic table, you're going to go from left to right and then from top to bottom. And you're basically going to do the opposite of that to find the previous noble gas. So you're going to go backwards. So from magnesium, let's go backwards and then go up. So once we do that, we were on the third period, we're going to go up to the second. And here we've run into a noble gas. We've run into one of these elements on the far right side of the table. And the element is neon. So just for an exercise, let's write the noble gas, let's write the electron configuration for neon. So again, if we're looking at neon now, I should have done it in red, but it's fine. For neon, do it over here. It's going to be 1s2, 2s2, and then 2p6. And neon's at the end of the block, so 2p6 is where we'll end. So if you compare this configuration to this configuration, you can see that this section right here, 1s2, 2s2, 2p6, is the same as this. So basically what we're doing with the noble gas configuration is just standing in, instead of writing all that out, we're just going to say it's the same configuration as we would have for neon plus this bit. So it's neon plus this bit. And that's all the noble gas configuration is. So you're never going to get a super long one because all of the early bits are sort of encompassed in this noble gas symbol right there. Okay, so let's practice with another one. So strontium. So this one is on the 1, 2, 3, 4, 5th level. So you know this would be a super, super long configuration if you had to write it out all the way with a full electron configuration. But instead, all we have to do is go backwards. So backwards, we were on the 5th, so we're going to go to the 4th level. And here we've run into our noble gas that comes before. So krypton is where we're starting with, and all we have to do is put krypton in our brackets, and then it's like we're starting at krypton and then starting to read from there. So if we're starting to read from here, we're at the end, we're at the end, and we're just gonna go down to the next level, and we can see that the next level is this level. So we're on the 5th level, we're in the S block, and we've got 5s1, 5s2, and that's it. So much easier than writing out the full configuration. Let's do another example. So here we're looking at cadmium. So again, just go backwards across the periodic table, and then you'll have to go up a row. And again, we're landing on krypton as our previous wow, I've been doing too much biology. Our previous noble gas. I was going to say amino acid there. Okay, krypton. Okay, so we've got krypton. We're going to keep, it's as if we just done this, 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 and this. It's like we just did all of that by writing krypton. So we're just going to go down to this next period. And again, we're still on the 5th one. 1, 2, 3, 4, 5. So we've got 5s2 because that's these guys. And then we're in the d orbital, or the d block. So remember, for the d orbitals, we're going to have to take a number off, subtract 1. So 4d is what we're going to write. And you can see that we're on 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 4d10. You also could have figured that out because it's the last one in the d orbital block. And so you know it has to be 10 because that's how many the d block can hold. And that's it for cadmium. So you still have to remember this tricky thing with subtracting 1 from the d block, but other than that, so much shorter. Okay, I think this is our last example. So let's give it a shot. So this one is going to be a little bit longer because remember, we can't go forward. We can't start with xenon. We can only go backwards. So we're going to go back across. We're going to land on krypton again. So back across this way and then up, and we hit krypton. So let's start with our krypton symbol. And then it's going to be the same thing. We're coming back to the next level, and we've got 1, 2, 3, 4, 5, 5s2, 4d, and we're going to go all the way across. So it's 4d10. And here is where we're going to hit our antimony. We did this one already. So we're in the p block, remember, and we're going to go pop back up to our actual level, which is 5. So we're in the 5p block, and we've got 5p1, 5p2, 5p3. And that's our final answer, 5p3. Or not, our final answer is this whole thing. And again, you can always check your work with these answers. You should know that these ones should end in S1, these should end in S2, these should end in P1, P2, P3, P4, P5, and P6. That's a 6. So we ended with P3, and that corresponds to the group that we're in. So that's a good sign on that front, and we're on the 5th level. Okay, I think that's everything. It is. So I hope this video helped with if you're feeling uncertain about electron configuration in general or noble gas configuration specifically. I would recommend, if you're feeling unsure about the filling rules, so like the Hund's rule and the Aufbau rule and the Pauli spin rule, to look at the slides that got posted, and there are questions to help you practice with those rules. And between this video and those slides, hopefully you should be in a good place for electron configuration. So let me know if you guys have any questions, and good luck studying this weekend.